In this final part, we will focus on high-LT radiation. And the first important concept that we need to introduce when we do high-LT radiation is the RB, the relative biological effectiveness. Where is this coming from? This we saw actually already at the very beginning, if you remember. We saw that the dose in radiation protection is expressed in sievert and not in gray, because you multiply the gray for a quality factor, for a weighting factor, radiation weighting factor, that takes into account the different quality of different radiation. Of course, those concept of weighting factor and sievert applies to radiation protection, so to the very low dose. Here we will speak in general of the RBE to explain why at the same dose you have different survival if you use, for example, X-rays in blue or heavy ions in red. And also you see already here the shape of the curve is not quite the same. Generally with the high LT, at least with very high LT, the dose response curve becomes linear. And that's, in a way, you understand already why, because the intra-track events in the microdosimetry model, the intra-track events becomes much more important than the inter-track event, because a single heavy ion can induce two lesions that will then lead to lethal lesions. So the inter-track, which is important for electrons, is not so important for ions. And then these become linear, it's more effective, and not the ratio of survival at the same dose, but the ratio of doses at the same survival is called RB. Be careful, because sometimes there is some confusion about that. The definition, the precise definition of RB is the ratio of the dose of the reference radiation, let's say gamma rays or X-rays, and of the test radiation, let's say heavy ion, at the same survival level. So you already see one problem with the concept of RB. We will see that RB, the problem of the RB is that it depends on so many factors. One factor is obviously the survival level that you choose. For example, if you take the survival at 10% in this specific case, which is just an example, it's not a real case, at this 10%, the RB will be 2.4, because this is the ratio of these doses divided by this dose. But if you take it at 1%, the RB will be 2. So the RB depends on the survival level where you look at it, or if you want, depends on the dose. So, I mean, and generally speaking, you see, if you have a large curvature in the photon survival curve, so if you have a radioresistant cell line or a radioresistant tumor, the RBE will be much higher at low doses than at high doses. Of course, the other problem that, among the many things where the RBE depends on, it depends on the energy, or if you want, on the LT. This is an example. These are carbon ions, Chinese hamster ovary cells, irradiated at different doses. Each curve here represents, the dotted line is the X-rays reference curve. So you see carbon ions at these energies is always more effective than X-rays. But note that there is something a little bit strange here. So if we start from this energy, 266 MeV per nucleon, 14 keV per micron, then you move to the blue, which is 76, lower energy, higher LT, more effective. Somehow makes sense, you can think, because, you know, the probability of having intra-track events will increase if I increase the LT. In fact, the following, the green, 11 MeV per nucleon, lower energy, higher LT is here. But when I go still down, 4.2 MeV per nucleon, 339 keV per micron, I don't go here, I go back. This is the so-called overkilling effect. We will see, this is very important. To understand this, we will spend some time to explain specifically this effect. So, as I told you before, the RB depends on the survival level. This can also mean depends on the dose. Of course, this is an example of dependence on the dose, but how steep is this dependence actually depends on the sensitivity of the curve to photons. Generally speaking, the highest RBE, so the RBE which is highest, will be the ratio of the alpha factors. So would be, let's say, the extrapolation at dose 0, which is the ratio of the alpha for X-rays and the opposite, of course, because it's a dose and alpha. So it will be the alpha of the ion divided by the alpha of X-rays. This ratio is the maximum RB. And in fact, this is generally what is used in radiation protection. If you want, the weighting factors in radiation protection come from the ratio of the alphas. You see? So you see one problem here with the multi-target model. With the multi-target problem, you are in trouble here because the alpha x is always 0. So essentially, because the initial slope is always 0, the RBE at 0 will be always infinite. So you see the problem of the multi-target model and the importance of the initial slope in the photon, in the X-ray survival curve. So if we now take these curves, these curves here, and we plot them as a function, when we plot the RB, now we can measure the RB at 10%. So we measure the RB at 10%. As a function of the LET, you get something like that. And we have seen this already. So initially the RB goes up because you see that the survival curves move to the left. The D0 moves to smaller and smaller values, but then suddenly comes back, and then the RB goes down. This shape, this bell shape, is characteristic always. If you remember, you have already seen it when we talked about chromosomal aberrations. We didn't plot the RB, we plot the alpha, but it's the same. You know, it will be the alpha of this curve, the alpha of the induction of chromosomal aberrations. We saw that it was going up and then was declining very highly. And this is always true with the additional problem you see here. Generally, you start from an RB. Of course, the initial value is 1, which is the same as at 0.2 kb per micron. This is in kb per micron, is the LET on cobalt gamma X-rays. So generally is small here, then goes up, then reach a maximum around 100 kb per micron, and then it goes down again here, goes down again when you go to very high LET. Please note that LET alone, we will see this later, LET alone is not enough to explain the curve. Because if you have ions at the same LET with different velocity, so different charge and velocity, you know, like protons and alpha particle at the same LET. So you have slow protons and high energy alpha and high energy helium ions. They have the same LET, but they have different velocity. Protons must be very slow, helium must be very fast. Their biological effectiveness is not the same. It's not the same. Okay, here you also have an idea, you see, of the energy that corresponds for electrons, protons, and alpha particles that corresponds to this LET. Of course, to go to this very high LET, it's impossible with normal radiation. You need very heavy ions. But this is, for example, important in space. And it's also important when you have stopping particles. You know, even for carbon, the LET can go up to many hundreds of kb per micron here at the end of the range of the Bragg peak. This is now a collection. You see, this is just a shape, but this is a real collection of all experimental data on all different cells with different ions. You see protons in pink, helium in blue, many on helium because, of course, you have alpha particles. Carbon in gray, also many in carbon because you have a lot of experiments done for the therapy. Neon in orange, also used a lot for therapy, and heavier ions in green as a function of the LET. This is the RBE10. This is a collection that you can find online. It's a database that we have made available, freely available, of all published data on cell killing. So it's in vitro, it's not in vivo, it's not animal data, it's not patient data, it's only cell data. But you see two things. The first thing, you see that the general trend is always the same. you go up until the maximum, and then you go down. So you always have increase in effectiveness, and then you have overkill. But then you see that the spread is huge. The spread is huge because the RB depends on so many parameters, including, as I said before, the charge and velocity of the ion. So generally speaking, the proton data here, you see, are higher than the neon data at the same LET. And the helium data here are higher than the carbon data or of the data for heavier ion. So one of the reasons why you see this large spread is the physics. But the biology is also huge. We have already seen, we will see more now, for example, that the RB depends enormously on the intrinsic radiosensitivity of the cells. Here I'm putting cells that are very sensitive and very resistant together. But in reality, now these are X-ray, always the CHO, and XRS5, which is deficient in non-homologous end joining. So it's very sensitive to X-rays. And you see that all the carbon ion curve that are so nicely spread here, they are all fall together. The RB is almost 1 here, while it's much higher than 1 here. So the RB depends very much on the intrinsic sensitivity. You see it clearly here. This is the RB for B79, that are these curves here for X-rays, you see, very radioresistant. This is the RB as a function of LET for Chinese hamster ovary, which are less sensitive, less resistant than B79 to radiation. And this is the RB for XRS5, is 1. So the alpha-beta ratio, as I mentioned before, is what makes the difference. Here, the alpha-beta ratio is very high. Eventually, it's infinite. Beta is 0 here. So this is alpha-beta ratio, which is infinite. In reality, you can always fit with a very small beta. So this is, you can say that it's not infinite, but it's certainly very high. Here, the alpha-beta ratio will be very small because beta is clearly very, very high. And you see, this is now the initial RBE plotted as a function of the beta-alpha ratio. So instead of alpha-beta ratio, of the beta-alpha ratio. And of course, the opposite happens. You see, it goes up. These are actually data from the PDE database, but refers to the same ion. And you see that if you change the beta-alpha, so if you go to radioresistant cell lines, you have a high RB. If you go to a low beta alpha, so high alpha beta, almost, you see, almost 0 here, which means beta 0, the RB goes down. But now let's try to understand the story of the shape. So why the curve goes up and then goes down? Why we have this strange coming back of the curve here, and which is then translated into an RB that declines at very high LET, and why 100 kV per micron is so important? Well, maybe an easier way to see this is to consider the let's take a linear curve. So let's take a single hit, single target model if you want. So which for heavy ions works quite well. Okay, so you have S that can be written as E2 minus D over D0. The beta term is 0, so everything is linear. But of course, the dose is the fluence time the LET. So you can write this survival as E2 minus sigma F, where sigma, LET divided by D0, you see, if you compare, so the LET divided by D0, is actually the cross-section. So you see now, this is a cross-section. So it's the product between the sensitive target and the probability that one ion through the sensitive target induce the effect, which is in this case is cell killing. Now, why we have this strange effect now? You see, this has been as a function of the dose, but if it was as a function of the fluence, you will see these curves going into this direction. So the cross-section increase when you go from low LET to high LET. Why increase? The sensitive target, let's say that is the nucleus, the sensitive target, the whole nucleus, is the same, doesn't change. But what changes is the probability that one particle through the nucleus can actually induce a killing effect, say cell death. Why increase with LET? Well, we have seen before. Now we are in intra-track regime. You see, it's a linear dose-response curve. So we are only in intra-track. The probability of having two lesions, okay, leading to an intra-track lethal event, increase if I increase the LET, because the mean free path becomes smaller and smaller, okay? So the probability of having two lesions close to each other increase until around 100 kV per micron. The mean free path of the ions is in the order of the nanometer. It's just like for the electrons, you remember the cross-section of the electrons. Now around 100 kV per micron, the mean free path of the ions is in the order of nanometer. So it's very likely that you induce double-strand break and double-strand break along the track, because every 2 nanometer you make a ionization. So it's very likely that you're inducing many double-strand breaks in line. At this point, what happens? That the probability reach the maximum value. This is the maximum probability, and the probability, generally speaking, cannot be higher than 1. Of course, you cannot have a probability higher than 1. So if at this point you have a probability which is higher than 1, the cross-section can only saturate, because the cross-section is a product of an area times a probability. So if P is 1, the cross-section is constant. Now, if you increase the LET at this point, but you want to keep the cross-section constant, you have to increase D0. And to increase D0 means exactly that the survival curve move back in this direction and the RB decrease. So this is the reason, if you see. I mean, a simple explanation, if you want, of the reason from the target theory point of view is simply that you have a cross-section, saturation of cross-section, and then while the cross-section saturates, in fact, these are examples of fluence effect curves. You see, with the fluence effect curves, you don't see the coming back. You see the saturation of the curves. And eventually, this is what happens if now you translate. You see, if you plot them as a function of the fluence, the cross-section now will saturate. But if you plot them as a function of the dose, the RB will go down. And in fact, this is what is observed. Actually, this is now the cross-section as a function of LET for many different cell lines, for hamster cell lines and many different ions. This region here is particularly complicated, is where you have the hooks. These are due to the fact now that at this very high LET, you can have the track structure matters a lot. In reality, it matters also here, we will see. But at this high LET, you can have cases where the same ion, if it is fast or slow, makes a very different effect. But in any case, you see the tendency is that the cross-section goes up, then saturates at high LET, and the saturation level is in the order of the size of the nucleus. As a matter of fact, you see, this is for mammalian cells. If you do the same experiment in yeast or in bacteria, you see that in yeast, you will have that the saturation cross-section is about 1 square micron, which is approximately the size of a yeast cell. And for bacteria, the saturation cross-section is in the order of 0.2 square microns, which is approximately the size of a bacteria. So you see that this model, let's say that the target model, if you want, somehow works well when you have heavy ions, because at that point, you can neglect the repair when you go to very high LET. But still you have these hooks that looks very strange, and they are related to this story. So the story that the LET alone is not sufficient to describe the biological effect. This is an experiment where you have the RB as a function of LET, but for 3 different ions, protons, helium, and neon. And you see that at the same LET, you have a very different response. Protons are much more effective than helium or neon. Neon will go down here if you can have this low LET. So the LET alone is not enough. You also have to take into account the track structure, because clearly these particles have different, they can have the same LET only if they have different velocity and because they have different charge. So at the end, the LET depends on the ratio between the square of the charge and the velocity. But if you change charge and velocity, you can have these effects. So generally, to describe these behaviors, people use the amorphous track structure models. That is, you take the track structure model, not stochastic track structure model, but the kind of track structure model that I also showed you in the physics experiment, in the physics lecture. You remember, where essentially you assume a 1/r² in the radial dose. You don't take into account the stochastic nature of the event. You don't do microdosimetry. You assume that it's like 1/r². You also assume that everything is due to electrons. So from the cell point of view, it doesn't matter if it is an ion or a gamma rays. It only matters the local dose. And from the convolution, all the biology, let's say for the biology, you want to use the X-ray data. So you don't include the biology in the model because you take the survival curve, the alpha-beta ratio, the survival curve from the X-ray data. So if you do this, if you remember, Robert Katz was one of the first to do an amorphous track structure model for the physics part. And then he used it to build now a cross-section for targets, that do not repair, like enzymes, viruses. Now the cross-section, the inactivation cross-section, can be written as 2π, because of course it must be an area, integral between 0 and r max, where r max is the maximum radius of the track, 1 minus s dr, r dr. R is the distance from the track, and the survival dr is the dose as a function of the radius. It goes like 1/r², and s is the survival that you can take now from the gamma rays. So what you get, in fact, I mean, if you do it, if you use, for example, the multi-target model, you see, you can say that the gamma rays survival, the gamma rays survival curves is described by a target, by a multi-target, and the ion cell killing is described by direct effect. This is the problem here, that if you, of course, you have sigma here, so you have a big problem in describing the curvature of the survival curve, because if everything is in the cross-section, at the end you will only have e to minus sigma f. But if you introduce a term which is gamma dependent, like a multi-target model, but could also be a linear quadratic model, and you write your sigma now in this way, then eventually you can arrive to a point. You see here, I mean, the relative dose contribution of the ion and gamma kill mode, where this is the ion kill and this is the gamma kill. This is the relative contribution. And then you will have the survival as the product of the ion kill and gamma kill mode. And this product will give you survival curves with the curvature. Of course, now you start to have many free parameters. You have sigma 0, which is the saturation cross-section. You have m, which is the number of targets in the multi-target theory. You have d0, of course, and you have k, which is which gives you the proportion of the two cell killing modes. If you use microdosimetry, how can you describe the RB? Well, again, you can use the general Keller-Rossi approach, when you say that the lethal events are given by AZ plus BZ squared, where now Z is the local dose. I mean, this is the point. Now, we can use microdosimetry now inside the nucleus, assuming that there are many domains interacting, the chromosomes, if you want, but not necessarily the chromosomes, because we have seen that intra-chromosomal exchanges can also be lethal. So they can be also subvolumes of the chromosomes. And S will be E2 minus L for the Poisson statistics. Now, if you have P domains, you can write this equation in this way, and then eventually in this way, where alpha 0 will be the initial slope. Beta is a quadratic term which is now independent of LET. Alpha is dependent on LET. Zeta 1D is the dose mean specific energy for single events. So it's the mean of the energy distribution, and D is the dose. So you see it's a linear quadratic, but here in alpha 0 and zeta Z1D, you will have the LET dependence. Z1D can be measured by TPC or calculated also from amorphous structure. And A and B, these parameters have to be calculated with some parameters. So the RBE eventually, the RBE with beta independent of LET, the RBE will have this form. So the ratio of the alpha of the two depends on the alpha beta ratio of the reference radiation. You see, can also be written in this way, where L is the LET and D is the sides of the nucleus. So you see at the end you need beta, you need the alpha values, you need the LET, and you need the sides of the nucleus, which is relatively simple. So it's a relatively simple formula for the LET. It's used now, the microdosimetric kinetic model is used a lot in particle therapy, in heavy ion therapy, also in Japan, especially in Japan, is used very much. The advantage we have seen already is that if you plot alpha versus YD, the dose average linear energy, then you don't see the track structure effect anymore. You see, it's essentially all points stay on the same curve. So the microdosimetric approach can solve the problem that you have seen here, where you have at the same LET, you have different RBE, but this is not the case when you take the linear energy, the dose average linear energy. In Europe instead, and actually is a model developed at GSI, the approach used is called the local effect model, which is very similar to the CATS model, but is a slightly different approach. Now, instead of making the integral over the radius of the cell killing, now what you do, you calculate the survival for every point. I mean, this is the radial dose distribution, this is the photon dose effect. So you count, these are different tracks. You can calculate the survival in every voxel here. It's of course, it's an arbitrary number, this one, you know, because it's like saying that there is a survival here, but then you can integrate. So now first you calculate the survival using a combination of the photon dose effect and the radial dose distribution, and then you integrate. And then at that point, you of course, this is the survival curve. You need to take into account, you need to introduce a threshold dose, just like you in the universal model that we have seen before for radiotherapy, because otherwise you don't have a linear end. But the results are very good. This model also reproduced the data very well. These are data, especially for carbon ion. So it's also used very much in Europe, in the clinics, for where you have the experience of the X-rays and you want to translate it into the heavy ions. So eventually, you see, even if you use saturable repair model, you can interpret the RB. You see, in this case, this is the difference between sublesions model, like the microdosimetry model, and the saturable repair models. You see, the RB in this case, in the microdosimetry, you have more one-track interaction of sublesions at high LET. So you have, as we have seen, that's why you go up in the. But in the saturable repair models, you will assume that high LET lesions are less repairable, and so that's why you have an increase in the RB. Then we will go back to the low dose rate in another lecture later. Finally, I just want to show you the neutron survival curves. Neutron is also high LT, so, and is also energy dependent, so not surprisingly, you have this behavior, and you have, these are spectrum of secondary charged particles produced by neutrons, especially protons, of course, and this is why make neutrons a high LT radiation too. You see that the survival curves have high RB compared to X-rays. And with this, I'd like to conclude, and we will meet to discuss this lecture next Wednesday. And the following, in the next lecture, we will still be at the cell level, but we will look at mutation transformation at the cell level.